So, good morning. In our last class, we have been discussing about this Kaiser window, right? And uh, I told you that I will be sending you the Bessel polynomial function table. I hope all of you have got it, right? So, please look into that. And if you have any problem, then let me know. Okay. So you will find that there are some values, say x, and for that x you will be finding the Bessel polynomial function ix. Okay. So herein we are basically talking about I0 alpha. So you whatever the alpha value you will be getting, this over here in the numerator, this function alpha under root of 1 minus 2n by capital N whole square, and in over here, so this alpha value is constant, as you all know, we have discussed yesterday. So as this number changes, so this number would be basically the x, and I of x you will be getting from the table. So please, so this is it. Basically you have to get the number, and just from the table you have to put in the number. Okay. Now coming to the types of the FIR filter, till now we have been discussing about different types of what you call methods, how to design the filters, and we had taken low pass filter as the example in most of the cases. In some cases we have also discussed about the high pass filters. Okay, so one thing I would be asking you, I just maybe forgot to tell you. Um, in the this week's assignment, you conduct this frequency sampling method example with high pass filter for high pass filter designing. Okay, rest of the specification it remains the same. Okay, so once you do that, you will be able to understand what is going on over there. Okay, if you have understood the basic principles or not, that I want to see. So in your home assignment you please do this thing. So yeah, today we will be starting with the different types of filters which are basically used in biomedical signal processing. Okay, so the first category of the filters, they are regarded as the smoothing filters. They are regarded as the smoothing filters. Usually, they are also regarded as the averaging filters. Both the smoothing filters and the averager filters, they are basically low pass filters. Okay, they are low pass filters. So, what are the applications of these smoothing filters or the averaging filters or the low pass filters? The four most common types of application of the smoothing filters are reduction of high frequency noises, reduce quantization noises, reduce motion artifact, and lastly smoothing of data. When you talk about high frequency noises, what are high frequency noises? Suppose you are calculating or you are acquiring ECG data. Okay, so ECG data usually it is having bandwidth in the range of 0.5 hertz to 100 hertz or 120 hertz, so whatever you talk about. Okay, so बात करना है तो बाहर जाके बात करो, don't talk in the class. So ECG data, ECG in the bandwidth, it is having a frequency range of 0.5 hertz and 100 hertz. Okay. Say for example, what happens over here is that we place the electrodes onto the surface. Okay. Now just beneath the surface, wherever you put, there will be some muscles, right? Now, muscles, when there is an action of the muscular activity, you will find that there would be some high frequency noises. So basically muscle activity, it will give rise to electromyogram, which we have seen in the flipped class. Okay. So we are having electromyogram. Okay. Now electromyogram, it can have frequency ranges starting from zero, not zero, in fact, 0. Again 0.05 I suppose, into few thousands of hertz. Okay. It may be 3 kilohertz, 4 kilohertz. So different books says different thing. So usually it is regarded as 3 kilohertz. Okay. So you are having from a very low frequency to the high frequency. Okay. Now our ECG signal, it is having frequency ranges of 0.5 hertz to 100 hertz. Now if we apply some filters also, it is possible that some EMG signals, which are high frequency signals, which are just above this 100 hertz signals, they may also creep into the ECG signal. Okay, it is possible because we are putting surface electrodes to acquire the ECG signals. Now this is the problem. So in those cases, the use of the averaging filter, it can help us in reducing the EMG signals. Okay, it can help us in reducing the this high frequency signals. Then our next point is the reduction of the quantization noise. So when we have this quantization process, what it does is that if you try to change that signal after the quantization process into the analog signal, you will find that we are getting staircase like stuff. Okay, so it appears as staircase signal. Okay, so in that case, what to do? We need smoothing or the averaging filter, and what this smoothing and averaging filter does is that it generates an envelope. It generates an envelope. Okay, so the signal what we get, it become smoothened, and due to that reason we are able to analyze the signal in a better way. Okay, so this is how it helps us in reduction of the quantization noise. Then the next one is motion artifact. So what does it say? Motion means when we move. Okay, so while you go for the ECG recording, you will find that on the chest they usually put bulb electrodes. Okay, so when you have these bulb electrodes, what happens is that when we are breathing, because while we are taking the ECG, we cannot stop the breathing. Okay, normal breathing goes on. So during the breathing, there are every chances that the electrode may move, and due to the movement of the electrode, there would be a change in the what you call impedance levels at the electrode skin interface, and that change in the impedance levels, it will result in the high frequency noise, incorporation of the high frequency noise in the ECG signals. So the noises which are being incorporated within the signals due to the movement of the body is regarded as motion artifact. I told you about this about for the ECG aspect. It can be true for the EMG purpose also. So in it can be true for the say needle electrodes also. In the needle electrodes, you can try to take the signal from a particular EMG muscle. So if due to some reason it moves during the acquisition process, then the motion artifact will be coming. So that's why you will find the clinicians and the paramedics, they try to minimize the movement of the electrode over the surface of the body by applying various techniques. So in the bulb electrode, a vacuum is applied so that uh, the electrode, it is stabilized onto the human body. Sometimes you will find that there are acrylate tapes. These electrodes are placed within the acrylate tapes and then they are placed onto the body. So there are several methods are being applied to stabilize the electrode onto the surface of the human body. Okay. Now, last one, smoothing of the data. You may have got good quality signals, but in certain cases you may be wanting to smoothen the data to get some meaningful results. I will give you an example over here. When we try to measure the heart rate, what we do is that there is a method called Pan-Tompkins algorithm. Pan-Tompkins algorithm, what it does is that we have an ECG signal like this. We apply a band pass filter whose bandwidth is approximately 16 to 21 Hz to extract the QRX complex. So when we do this, we get something like this. Okay. Or in some cases, you can also get something like this. Okay. It depends how you are processing. So let us take this as the example. We get this kind of thing. Next, what happens is that we do squaring. So what happens? Across this baseline, there are bipolar signals. So then it becomes unipolar signal. Something like that. Okay. Now the smoothing filter is applied, and while it is being applied, it becomes a hump. And if you see a series of these ECG signal, then you will get something like this. Okay. So you collect a range of the signals and then you try to find out the number of the peaks within that given period of time, and from that calculation you can find out the heart rate. Okay. So this is, so here see, we started with an ECG signal which we considered that there are no what you call noises. Okay. But to get some meaningful result, we had to apply a smoothing filter over here. Okay. So after getting a typical type of the signal, then we went for the calculation of the heart rate. Okay. Now lastly, we have power line interference, which is also which is basically been what you call eliminated using the notch filter. Okay. Which is basically been eliminated by the notch filter. However, if you see the notch filter, what is the nature of the notch filter? Yeah, so notch filter, it helps us in eliminating a very narrow bandwidth of band of frequencies. Okay, so when we talk about the power line frequency in India, the power line frequency is 50 hertz. Okay, in India, the power line frequency is 50 hertz. Okay, so if you apply a notch filter, basically you will find that there is a combination of a low pass filter and then a high pass filter. Okay, so due to this combination of the low pass filter and the high pass filter, you will find that there is some smoothing of the data, and especially the smoothing of the data, it is around the frequency band which we want to suppress. Okay, which we want to suppress. So notch filter, it is not a smoothing filter in practicality, but it can incorporate some kind of smoothing while you are processing a given signal. Let us take an example. Again, I will take the ECG signal like this. Now over here, let us consider that we are having the power line interference. So over this signal, you will find that this power line interference 50 Hz signal, it is being overriding onto the signal. So when you apply this thing, so what will happen? Our ECG signal, it will almost look similar to that of the original signal what we drew. Okay. So what has happened? If you see in the initial case, there was too many corrugation. Now those have been subsided. Now when they are being eliminated, it is nothing but you are smoothing the data basically. So notch filter in itself is not used for smoothing filters as a smoothing filter, but inherently it will show some kind of smoothing effect. So you have to keep in mind. Okay. And why that is so? Because it is stopping a very narrow band frequency components within the signal, and due to that reason it is able to induce some smoothing if the signal is being corrupted with that narrow band frequency components. Okay. Now let us take an example and let us create one averaging filter. Let us take the time n and let us take the number of students entering into the class. Say for example, at 0 instance time, 2 students have entered. In the next moment, 3 students have entered. In the next instance, 5 students, 1 student, 3 student and 5 student. In the region 2 and 3, you will find that there was an abrupt increase and then abrupt decrease in the signal component. So that is simulating the high frequency noise. Okay. Now let us create a 3-point averager. So how it works? So 3-point averager, what it does? x1 plus x2 plus x3 divided by 3. It is a simple average. What you do? So let's start with 0. So when we talk about the 0 instance n equal to 0, we have two values. So what about the previous two values? N equals to -1, -2. They are 0 divided by 3. So we get a value of 0.66. Okay. देखो तो कौन ये कर रहा है, फिर दरवाजा बंद कर दो. In the next instance, what is happening? We are at 3. So 3 plus 2. So n minus 2. N equals to -2 from here. 0. We are getting this thing. When we come to n equals to 2. See, 5 plus 3 plus 2 divided by 3, it is coming to the 3.3. Next value if you see, 3. Next value, 3. So see, over here it is trying to, we are basically getting a smoothened curve. Okay. However, this spike, it has been significantly reduced if you see. Okay. And another thing is that again, if you move forward, you are getting another whatever the value you are getting. Now in the first two case, if you see, the values are quite lower. Okay. Now why this is so? This is because whenever you are using a system, at the initial phase of the system is not stabilized. The output of the system is not stabilized, because these kind of systems, they are operating with the previous values. Okay, with the previous values. Here we were taking three values. So in the first case, apart from the first case, 3 minus 1, two values were missing. So it took the filter to be stabilized for 2 units of time. Okay. If I ask you, design a 5-point averager, moving averager, then 5 minus 1, it would take 4.8. Right. So if you see over here, so what is happening, as you are increasing the taps, okay, what is 3.5 point? These are nothing but the taps. Okay, order of the filter basically. So as you increase the order of the filter, the longer will be the time needed by the filter to get stabilized before it can give you some stable results. Okay, so this you should keep in mind, whether it is in the FIR filter, whether it is in the IR filter. Okay. So what we have done basically, if you see, yn is equal to 1 third of xn plus x of n minus 1 plus x of n minus 2. This is what we have done. So this equation, this differential equation, is the equation for the 3-point moving averager system. Okay. So if you try to find out the, what you call, transfer function, then we will get yz equals to 1 by 3 xz plus xz into z inverse plus xz into z to the minus 2. Okay. So what would be with xz, yz by xz, it would be equal to 1 by 3 1 plus z inverse plus z to the minus 2. So see, by using the simplest formula, averaging formula, which you might have been studying from class 3-4, you have been able to design a filter itself. Right? Now coming over here, some types of, some examples of the FIR filter. I have already talked about the 3-point averager. Okay. Then after doing that, you can just implement the filter, design the filter. Designing we have already discussed, right, previously. Right from realization, we have already discussed this thing. So I think you will be able to do it. If you are not able to do it, just let us know. Now we will discuss it in some additional classes, because I don't think we will be getting some classes to for the revisions. If needed, we will conduct one extra class for the revision. Then Hanning filter, what you see, xn plus 2 of x of xn minus 1 plus x of n minus 2. Here the central value, it has been given more what do you call weightage. Okay, so if you see the coefficients 1 plus 2 plus 1, 4, so it becomes 1 by 4. In any kind of averager, the addition of the coefficients will be used to divide that addition or the polynomial function. Okay, so in this way, if you see, we have been able to design this Hanning filter quite easily. Okay, now once you have done this, we can easily find out the amplitude response, phase response. Right? Method I have already told you, so I am not going into that. Right? Now least square polynomial smoothing. It uses some tap weights. Okay, so L, it is equal to basically n by 2. This L is basically tap weights minus 1 divided by 2. So basically this tap weight size is the length. So please don't confuse with the length of the filter and this cell. Okay, tap weights is the length of the filter, and this L is basically the order of the filter, or length minus 1 divided by 2, or order of the filter by 2. Okay, so herein same thing, if you see 1 by 35, and then you are having, see, 17, which is the middle value, and the other values, you see, you are having these values repeated. Okay, in the next case, 7 is the central value, and on other both of the sides the values are repeating. This is the same in all the cases. So when we are talking about least square polynomial smoothing, which is basically is for the low pass filter design, we have to remember these step weights, and then you can design the filter easily. Then coming to the notch filter, in the notch filter it is given 180 samples per second is the frequency. Is 0 at 2 pi by 3 removes 60 hertz line interference. ये लीन हो गया, this should be line frequency. So this is the equation. You find out the values of this z, where zeros where they are being placed, and then you get the modulus of h omega and minus of h omega. Just wait a minute. Hello. Sorry. Okay, so herein, if you see, we have talked about 60 hertz. 188 it's given 60 hertz. It's because I have used the what do you call example from the biomedical signal processing by Tompkins. So which is basically an this American author. So over there we have 60 hertz power line. Okay, so hence the example of 60 hertz has been given. However, if I give you say 50 hertz signal and if I ask you to design the filter, you should be able to design the filter. Okay. Any doubt? We will not be able to design the filter. We have already discussed that in the how to design the filters by pole zero placement. FIR, it's pretty easy. All the poles will be at the origin. That's why if you see in FIR filters, no poles are being shown because it is understood that poles are at the origin. Okay, but for your exam purpose, please put the poles. Okay. So मनोज इनको ऐसा एक क्वेश्चन दे देना हाउ टू डिजाइन द FIR फिल्टर कोई एक पर्टिकुलर इसमें लेट देम डू इट ओके नाउ फर्स्ट वन वाज द your low pass filter. The second are the derivative filters. So derivative filters are basically high pass filters. So you keep the acronym in mind, HD. We all are quite familiar with the HD, these high definition systems. So in the HD systems, what is happening is that a high pass, it tells that a high pass filter is a differentiator. Okay, a low pass filter, it is an integrator, and a high pass filter, it is a differentiator. Okay, so here, how do you find out basically differentiation? What, if I ask you find out this differentiation of x, what you will be doing? dy by dx. यहाँ पे y ये होगा dy by dx, right? So y का differentiation it is dy by dx. So what is dy by dx? The change in the value. So it is nothing but x of n minus 1 minus difference of x of n. If you put difference, so जो भी ज़्यादा होगा वो ले लेंगे divided by difference in time. So वहाँ ऊपर अगर हमने लिया है, so say t1 minus t0. Alright. So if you see this equation, what is this? Same thing. Xn minus x of n minus 1 and capital T, it is a time period, it is nothing but time का value, time का जो difference है, right? So this is the simplest simplest derivative systems. Okay. Now one important thing over here is that if you see our 0 is here and over here we do not have anything. So signals are getting amplified. So because of that, what is happening? High frequency noises, if they are present within the signals, they will be getting amplified. And to avoid that, this 3-point central difference system has been created, which says x minus of x of n minus 2. यहाँ पे देखो x of minus 1, it has been completely removed, x of n minus 2. So what is that difference in time? It would be 2t because xn minus 1 में हो गया 1t and then x of n minus 1 and x of n minus 2 another t. So both will be added up, so you will be having 2t. So by this simple modification, if you see, we are having another 0 at the high frequency over here also at pi. So what it allows is that herein the high frequency components are not amplified as in the case of the 2-point difference system. Okay. Now then we have this least square polynomial derivative approximation. Okay. This is the equation. Hello. Sorry. So least square polynomial derivative approximation. So here we already this is the equation, and then this is the implementation part, and this is the pole zero plot for this equation. Okay. Now again, just like in the least square polynomial smoothing approximation, over here also we have some tap weights, and these tap weights are basically the length of the filter. So it will give you the length of the filter. But the interesting thing, if you see, the central point over here are all 0. Okay. And another important thing is that if you see, the left hand parts, they are positive, and the right hand parts, they are the negatives. So there is a gradient of positive to negative. Whenever such kind of filter exists, these filters, they are generally regarded as gradient filters. So these filters, they are gradient filters. Okay. In image processing also, when we will be studying image processing, you are having this semester or next semester? Next semester. Over there also you will find that you will be getting different types of gradient filter. So those gradient filters can be hello. Sorry. So over there also you will find gradient filters, but over there, since we are working with the 2D signals, the nature of the gradient signals, gradient filters can be different. Okay. So, but over here, the only direction is a single direction. This thing. So in 1D gradient filters, you will be having not much variation. So two types of variation would be there. Sorry. So one is positive to negative, as you go from left to right, positive to negative. Also we can have negative to positive gradients. Okay. Now the next type of filter, it is second derivative filter. Now in this second derivative filter, what we are having? We are having this first derivative filters. If you see over here, 1 minus z to the power minus 2, 1 minus z to the power minus 2. Okay, you get it multiplied and you get this type of filter. So you can either implement this filter in the cascading form, or you can implement the filter in the form of 1 minus 2z to the power minus 2 plus z to the power minus 4. Okay. So this filter would be a second derivative filter. So if you want to go for the third derivative filter, just multiply with 1 minus e to the power minus 2 again. So you will be getting the third derivative filter. Okay. So if you see, In most of the cases, this 3-point central difference filter, it is being promoted as compared to the 2-point difference filter, because of the reason which we have discussed just now, that 2-point difference filter, it can amplify the high frequency components. Okay. With this we complete this chapter. So if you have any questions, we can discuss.